right, so let's go ahead and date it and then write down our 6 steps that we're going to do with this. All right, so November 16th. And this is optimization problems. And then let's put day 1, because we're going to take 2 days to do this. I'm going to do, since the problems take so long, we're going to do 2 examples today. We'll do 2 examples tomorrow. All right, now I am going to be very demanding in what I expect from you when you do an optimization problem. There are 6 steps, and if you label each one of those 6 steps, you're going to be a whole lot more inclined to get the answer right. Okay, so our 6 steps. As with any related rates, optimization, any of that, I do expect you to obviously draw the picture. That's not really a step. It's just you've got to start doing that. All right. You've got to also write down your given. And in this scenario, I'm going to call it a want. Okay. As opposed to find. In related rates, we were given something and we were told to find a rate. All right. In optimization, I like to use the word want. You're given a bunch of information and you want to maximize something. You want to minimize something. All right. So what am I wanting to do? That's the only reason I'm using the word want. Okay. So the first thing that we're going to do is we are going to solve the given. So you've got to be able to identify that given from your problem. You're going to solve the given for y. Okay. Step 2, we're going to plug into our want. So whatever we get for our y, we're going to plug it into our want. All right. Then at that point, we're going to do our first derivative, and we're going to find those critical points. Okay. All right. And then the critical points we know is here, let's put in here, which is the answer. Now, honestly, at that point, you're going to have your answer to the problem. All right. However, you know, when we find critical points, sometimes you find 2 values, and with other types of solving equations, you get extraneous roots, things of that nature. Okay. So you have to go through a verify to verify whether or not that works. All right. So then our 4th step is going to be to verify. And we're going to verify our answer with the second derivative test. And I am going to, or with our second derivative, I won't necessarily say second derivative test, but with our second derivative. And the reason I say that is because that's going to be the easiest way to do it. It's really quick. It's short. All right. We've already practiced verifying things with that second derivative. That was on the last quiz we took. So you ought to be really good with the notation and what it looks like. On rare occasions, that second derivative is not going to work. Nice. And when it doesn't work nice, then you go back to your first derivative test. Okay. Your step 5 then is going to be find any remaining dimensions, just whatever the problem is asking for. So it could ask for miscellaneous dimensions or information. You just want to definitely make sure that you are answering the question for whatever it asks for. All right. And then our 6th step is going to be to write your therefore statement. And I did that so I don't have to write it down. All right. Write a therefore statement that answers the question. All right, so now after you do enough of these 6 steps are going to become natural. Like you will memorize them, you'll do it. All right, and you're going to label in every one of your answers. So your homework tonight should look identical to the way I do the problems in class today. I'm going to label each one of these 6 steps. And by the time you get done doing homework today and tomorrow, you will have those 6 steps memorized, and it just should be a natural process for you. Okay. All right, so I'm gonna pause this a little bit. I'm assuming you're staying up with me. If at any point in time I get ahead of you, I'm writing too fast, I move something away from the screen, just let me know. All right, and I can put something back up. All right, so first question here. And like I said, I've typed this out so that would save a little bit of time so that I'm not handwriting. All right, I will pause here a little bit so that you can write it down, because you definitely need to have this. written. So I'm going to pause. I'm going to stop talking while you write for a minute. Although I guess I could read it. Okay. It says a farmer plans to fence a rectangular pasture adjacent to a river. All right, this is your pretty common, straightforward optimization problem. The pasture must contain 180,000 square meters in order to feed his herd. What dimensions will require the least amount of fencing? All right, notice I put this in all capital letters. All right, so that you won't get that on a test. You won't get that in any type of testing environment, but just for the lesson here. Okay, now if I'm wanting to find the dimensions that require the least amount of fencing, this is going to be a minimum problem. I want to minimize. All right, because like obviously stop and think about this. If I was buying fencing, I don't want to buy tons and tons of fencing and have way too much pasture that I really need for my herd. All right, you'd be wasting money on your fencing. All right, you'd be giving up land that you might be able to use for something else. Okay, so we want to minimize the amount of fencing to make that pasture the most optimal that it could be for the given herd. Okay, that's the whole point of an optimization problem. Okay, a little bit later, probably not today, maybe tomorrow sometime, we'll actually talk about some more real world applications. Not that this isn't, but this is designed as a story problem, okay, for you to get the idea. And then tomorrow we'll go into, okay, well, so let's think of some real world applications of where they actually use this and who uses these optimization type problems. Okay, so let's go through and look here. Rectangular pasture adjacent to a river. All right, that's going to set you up for what your picture is going to look like. Okay, so let's say here that that's my river. All right, rectangular pasture, okay, adjacent to the river. So I'm going to have a rectangle. Okay, so pretty much there's my picture. Okay, the pasture must contain 180,000 square meters. All right, well, square meters tells me what? That tells me the area of this. So let's go ahead and just put that in the middle, 180,000 meters squared. All right, what dimensions will require the least amount of fencing? Okay, so I definitely want to do least amount of fencing. I'm going to do that in green. The least amount of fencing. Okay, so that tells me it's a minimum problem right there. Okay, now dimensions. I don't know what the dimensions are of this. I'm trying to figure them out. Okay, it really doesn't matter how I set them up. I generally put X here, and then if I put Y here, then Y is also over here, right? Because this dimension and this dimension would be the same. Okay, so let's identify our given. Okay, so our given, what did they give us? They gave us the area being 180,000. Well, based on the way I have labeled this problem here, my area is going to be X times Y, length times width, because it's a rectangle, and that's going to be equal to the 180,000. All right, so I have an equation. From the given information, I can write an equation. All right, now what am I wanting to do here? All right, well, we said with this least amount of fencing, all right, that tells me that I am trying to do a minimum problem. I'm trying to minimize. All right, now, amount of fencing. Okay, well, that means I would put fence here, I would put fence here, I would put fence here. Well, when I start going around the outside, that is the perimeter of a shape. So I want to minimize my perimeter. I'm trying to minimize the perimeter. Now, again, I need the equation to go with this. All right, so I'm just going to do it in terms of letters. P for perimeter is going to equal to, okay, well, what would my perimeter be of the way I have drawn this? Well, I've got an X and I've got two Y's, because if I go X plus Y, then I would have the perimeter. So it's going to be X plus 2Y. Okay, so these two equations are what you're going to generate from your picture and from the information that's in the story problem. Okay, now I do that part first and I set that out to the side because I need all that information before I can start my 6 steps. Okay, now step number 1 was solve for the given. All right, solve given for Y. So I'm going to literally label it solve given or y. Okay. And you're going to do this on your homework, on written test. We will be back to school. We're not going to be virtual for the rest of the year forever. So when we go back to school and when you take a written test from me, I'm going to expect all the steps labeled like this. All right. Now, so assuming that you wrote your given equation right, I'm going to take that given equation, xy equals 180,000. And I'm going to solve for y. My choice. This is just the way that I do this. I solve for y. So I divide by x. So 180,000 over x. Okay. Now I think normally under normal circumstances, I probably go down. I'm going to run out of paper here. So I'm going to go across and then I'll go to a new piece of paper. All right. Step 2 is plug into my want. Okay. So I'm going to plug this into my want. All right. Now my want equation, initially, I am going to write it with just a p equals x plus 2y. All right. However, writing it like that, I'm not in function notation. All right. And everything that we've done, we like function notation. I want to turn this into function notation. To do that, I would need this all to be x's. All right. And I could call this p of x, my perimeter function. Okay. So when I plug this in, okay, so I'm plugging this in here. So I'm going to turn it into function notation. This is extremely important. P of x. Because I'm going to have this all in terms of x when I am done. All right, x plus, all right, 2, I'm going to replace y with what it equals. So 180,000 over x. All right, now hopefully now you can see this is an equation all in terms of x. And by doing p of x, I've turned this into function notation. All right, now let's go ahead and simplify this out a little bit here. So let's go p of x is equal to x plus, let's take 180,000 times 2. That'll be 360,000 over x. Okay. All right. Now at this point, I think I'm going to go to a new piece of paper because it's going to get kind of long here. All right. Now keep in mind, this is going to be my p of x equation. I'm going to rewrite it in the next step since I'm having to go to a new piece of paper. Okay. All right. So our third step is going to be our first derivative and our critical points. All right, now, like I said, I'm going to rewrite that function that I just had on the other piece of paper. So p of x, x plus 360,000 over x. All right, now, if I'm going to take the derivative of this, this is a quotient, all right? This is just a little trick. Do not attempt to do quotient rule right here. It's going to make the problem way too hard. So what I'm going to do as we go through this, I'm going to show you some little tricks. It just makes the problem a whole lot easier. All right, and a lot of you do this anyway when you're calculating the derivative. I'm going to move that x up and make it negative to make my derivative a little bit easier to do. So p of x is equal to x plus 360,000 x to the negative 1. All right, this is way easier to calculate a derivative on than this right here. And I'm in the classroom by myself and the lights just went off. Okay, all right, so when I wave my arms, I'm just turning our lights back on. All right, now we're going to take our derivative here. Okay, so derivative of x is going to be 1. Okay, derivative here, pull that down, just nice little power rule. So it's going to be minus 360,000 x to the negative 2. Okay, pretty simple there. Now, what do we do in our next step? After we calculate that derivative, we set it equal to 0 to find the critical points. All right, but I don't want to try to solve something with a variable with negative exponents. All right, that's going to make solving for x a little bit more difficult. So again, I'm just going to try to do something that's going to make my life a little bit easier. I'm going to move this back down to the denominator. So my derivative then is going to look like 1 minus 360,000 all over x squared. All right, if I've got an x to a positive 2, that's going to be a whole lot easier to solve than an x to a negative 2. Okay, so I'm going to set this equal to 0 now. So 360,000 all over x squared equals 0. Okay, so I'm setting it equal to 0, finding those critical points. All right, I'm going to go ahead and move this to the other side. Show some steps here. Make it a little bit easier. Multiply both sides by x squared. Okay, so x squared equals 360,000. All right, now take square root of both sides. All right, technically, when I take square root of both sides, I would get what? X equals plus or minus 600. All right, but what do we need? Like, I'm trying to get dimensions, right? So it's not going to be the negative 600. So then I know my X right there is 600. Okay, now technically that's going to be our answer. Okay, but I don't know for sure. I need to verify whether or not that really works. Does it really minimize? And we're going to verify that using that second derivative. Okay, so next step, step 4, is verify. All right, and I am going to require that you verify with the second derivative. It is a whole lot easier. You just got to trust me on this. All right, I'm setting this up. I've tried to design these, or the way we're doing them, to make it as easy as possible for you. Okay, so let's write my first derivative down. So let's see which one. I want this one because it's going to be the easiest one to manipulate. So 1 minus 360,000 x to the negative 2. I want that one because, remember, it's going to be easier to take the derivative here. Okay, so if I'm verifying with my second derivative, I need to calculate that second derivative. So second derivative. Okay, so when I take the derivative there of 1, it goes away. Power rule here, negative times negative is going to make it a positive. Okay, so 720,000 x to the negative 3. All right, and again, if I'm going to plug a value in to test it in the second derivative, wouldn't it be a whole lot easier if this was a positive exponent? Okay, so go ahead and take that second derivative and rewrite it so that it's 720,000 over an x to the third. All right, and then that, when I plug something in, I'm going to real easily be able to check it, test it. All right, now the steps that are crucial. Okay, the steps that are crucial. This was on the last quiz. All right, I want these laid out exactly like this. We've got a second derivative. I'm testing my answer of 600 in that second derivative. All right, and then here, I expect you to do this in your head. Okay, you got a positive number on top. If I've got 600 raised to the third power, I really don't care what it is. It's going to be positive. I've got a positive divided by a positive. I know this is going to be greater than 0. That's the only thing you need to show on the AP test. Okay, all right, now from there, I can draw a conclusion. All right, therefore, x equals 600. This is where I don't want you to do an ordered pair, okay? Or this is in the context of a story problem. So x equals 600. All right, when this is greater than 0, it is a minimum. So x equals 600 is a minimum. All right, and so there's my verify. It checks. That's what we were supposed to find. We were supposed to find the minimum perimeter. Okay, so when x is 600, we're going to have minimum perimeter. All right, step 5 is find whatever other dimensions that I might need, because we were wanting dimensions of this pasture. Okay, so let's see. Let's do the area formula, because x times y was, what was that, 180,000? And I know what x is now. X is 600. So 600 y equals 180,000. This is just basic arithmetic. Solve. I get y equal to 300. So now I've got my other dimension. Okay, so straightforward. And step 6 was your therefore statement. So I'm going to come up here, write down my therefore statement. All right, so what do we have? We have, what was this in? This was in meters. So 300 meters by 600 meters will require the least amount of fencing. And then there's my therefore statement. All right, now across the board, I mean, that's all there is to this. There are 6 steps. All right, and like I said, I've tried to give you some hints, suggestions. When I have something like this, don't try to do a derivative like that. Move it up, make your derivative easy. All right, but then when I want to solve this derivative set equal to 0 and solve, again, you don't want negative exponents, move it back down. So there's little tricks in here on how to make things a little bit easier. Same thing here. All right, trying to plug a number in here with that negative exponent would make it hard to do the math in your head. So manipulate it so that the equation is easy for you to mess with. Okay, so For the most part, that was straightforward. Are we all doing pretty good on those 6 steps? I'll pause. Anybody have questions? All right, I'm kind of hoping that this is kind of laid out straightforward. Okay. All right, so the pasture along a river, really common type problem that you're going to encounter. Okay. Now let's go ahead and look at a second example. Okay, again, I'm going to pause here a little bit, give you time to write that down. I'll go ahead and read it. In this one, we've got a manufacturer that wants to design an open box. Okay, so lots of important information there. Open box having a square base and a surface area of 108 meters squared. What dimensions will produce a box with maximum volume? All right, so a lot of different pieces and parts here. All right, that wasn't too long of a sentence, so we'll go from there. Okay, let's see. Important things in this. All right, the manufacturer wants to design an open box. Open box basically means no lid. Okay, no lid. All right, having a square base. Okay, square base. And let's switch colors here. A surface area of 108 meters squared. And I'm wanting to find the dimensions that will produce a box with maximum volume. Okay, so those are all the important things here. All right, now let's go ahead and work on our box, drawing it. Okay, so I mean, how you draw the box, it's the 3-dimensional box. Not necessarily that I'm going to be really good at this, but let's try. I'm trying to make a square. Okay, so if this is a square, then I've got to have this side equal to this side. Okay, I don't know how tall this is going to be. Let's just go up to here. Those should be kind of parallel. Those should be kind of parallel. Everyone draws 3-dimensional shapes differently. Okay, I think it got narrower at the top. We're going to assume that it's not. All right, so this is, I just happened to draw it in this manner. All right, my base is a square base. So this side and this side has to match for that square base. All right, now my height, I have no clue what it's going to be. I'm actually going to let it be an H just so that it's sitting up right. There's my H. Okay, now it does not have a lid. Okay, I can't really show that, but it does not have a lid. Okay, now let's go through and do our given. All right, now, if they have given us a surface area of 108 meters, okay, so let's go ahead and write down surface area 108 square meters. All right, but I need an equation. Now, this is where you got to pay attention to the fact that it says open box. You're not going to take the surface area for a rectangular prism or a square prism. All right, you're going to think about what is surface area. Well, what is surface area? It's each one of the surfaces added all up, right? So I clearly have a bottom to this lid. Well, what's the area of the bottom? The area of the bottom, it's a square. So x times x, okay? So x squared. That gives me the bottom, the surface area of the bottom. All right, now I have 4 sides. I've got a front, left side, right side, and a back side, right? And it's a rectangle. So the area of a rectangle is length times width. So x times h. And how many sides do I have? I have 4 sides. I've got the front, left, and right, and the back. So I'm going to add to that 4 of the sides. All right, I don't worry about the top. All right, so that's why I'm saying you're not just going to randomly take the surface area formula for a rectangular solid, because this refers to an open box. So there is no surface area there on the top. All right, and that has to equal 108. So the equation that you're going to get from the given, you're going to have to create. Okay, now what do I want? Okay, well, I'm wanting to maximize my volume. I'm wanting to maximize the volume. Okay, now across the board, volume of a three-dimensional shape, three-dimensional box like this would be length times width times height, right? So L times W times H. But again, you don't want that generic formula. You want it in terms of whatever picture you just drew. So the length, width, height. So X times H. So my volume, I'm going to put it over here, is going to be equal to X squared times H. Each one of the three sides multiplied together. Okay, so you do have to understand what the volume of a cube is or what the surface area is. You need to understand those things, but you're not necessarily just going to straight memorize the formulas and use the generic formula, because each problem is going to involve something different. All right, so now once you did all of that, once you get your picture drawn, you've got your given, you've got your want, all right, then you're ready to start with your 6 steps. Okay, we're going to label them, okay, every time here. So we're going to solve the given for, now this time I don't have a y, right? I don't have a y, and I said solve for y. So you will vary each one of your problems a little bit, but you've got to solve that given for something. I'm going to choose to solve it for my h. Okay. All right, so I'm going to take that equation that I wrote in the given, x squared plus 4xh equals 108. Okay, I'm solving for h. So let's see, subtract the x squared from both sides. So 108 minus x squared. I'm solving for h. I want to divide both sides by that 4x. So h is going to be 108 minus x squared all over 4x. All right, and so for the most part, as long as you've written that given correctly, then the algebra there is not too bad. Okay, again, I'm going to go sideways just because I'm running out of room here. Next step is going to be to plug into our want. Okay, so my want equation, again, I'm going to write it down initially not as a function. I'm just going to write it down the way I found it from my picture. So v equals x squared h. Okay, now I want to turn that into function notation because I want this all in terms of x. I want it all in terms of the same variable. That way I can take the derivative, find those critical points. So it becomes v of x at this point because I'm going to function notation. All right, I'm going to have my x squared, and then I'm going to put in for h 108 minus x squared over 4x. All right, and then just a little bit of like algebra simplifying here. Let's see, could we cross out an x here? I don't want to mess up the problem too much, but I can cross out that, and then could I at the same time distribute the x in? So v of x is equal to like 108x minus x to the third all over 4. Okay. Now I want to do some more. I'm going to do it here before I go to the next step, I think. Look at that. Do I want to take a derivative that looks like that? I don't. I don't want quotient rule. Okay. I know it's got a 4 on the bottom, but I don't want quotient rule. I want to make this as simple as I possibly can algebraically before I attempt to take that derivative. Okay. So if this is, I've got subtraction on the top and I'm over 4, can't I break that up into 2 fractions that are being subtracted? Okay, so v of x, couldn't I have 108 over 4x minus, write this as a coefficient, 1/4 x to the third. Everybody see what I did there? I just broke that up into 2 fractions. I used the 108 and the 4 as coefficient. I used the 1 here over 4 as a coefficient. All right, and then I am still running out of room here. I think 108 divided by 4 comes out to be like a nice 27. All right, so 27x minus the 1/4 x to the third. All right, that is going to be a whole lot easier there to take that derivative. Okay, and that's what we want. You want this as simple as possible for the next step. All right, so I'm going to go to another piece of paper here. We'll get step 3 going. All right, step 3 is where we actually start our calculus. We're going to do our first derivative. We're going to find some critical points. All right, now just so we've got something to look at here, I'm going to rewrite that equation I just had. V of x, 27x minus 1/4 x to the third. Okay, so from here, I want to go ahead and take that derivative. So v prime of x, all right, that 27x is just going to go to a 27. Over here, I'm going to do power rule. So I'm going to have minus 3/4 x, and then subtract 1 from that exponent. Okay. Pretty straightforward. There's not anything really easier that I can do to simplify this. So I'm going to go ahead and set that equal to 0 and solve to find those critical points. All right, let's see. If I move the 3/4 over, it'll be positive. So let's do that. So 27 equals 3/4 x squared. All right, you guys should be good with the algebra here, but just in case, multiplying by that reciprocal is the easiest way to get rid of that 3/4 right there. Okay, just going back over some of that basic algebra. So 27 divided by 3 times 4 is going to give me a 36 there on that side, and then an x squared over here. All right, again, technically, when I take square root of both sides, I do get plus or minus 6. But what are we talking about? We're talking about dimensions of a box. So I know it can't be the negative number. I know x is going to be 6. Okay, now technically, that probably is going to be the answer. Now, will it be the answer absolutely positively every time? No. If I only get one answer, then yeah, probably. But depending on what this derivative looks like, when I find my critical points, can't I find more than one critical point? And in which case, one of them may give you a maximum and one of them may give you a minimum. So the verifying really does, I mean, you really have to do that to verify what your right answer is going to be here. All right, so step 4, we are going to verify, and we're going to use second derivative. All right, and the reason, another reason why I definitely want you to do it this way is when I'm grading this, when you go, we come back in class and you start doing this by hand, you're going to actually, I'm going to grade that second derivative just to see if you've calculated it correctly. All right, so let's write the first derivative down. I'm just rewriting that first derivative just so we have something to look at here. I mean, I know I could look at it right there, but okay, second derivative. Okay, so I take the derivative of that 27, it goes away. I take the derivative here, I'm going to have a negative 6/4 x. Okay, negative 6/4 x. Okay, at this point then, I'm going to want to plug in my 6. So second derivative at 6. Okay, now I'm going to take a negative 6/4 times a positive. So negative times positive is going to be negative. So that's all I need to know. I don't need to know the exact value, but I know that it's less than 0. So that's the only thing I have to write. And then, therefore, from that conclusion, when my second derivative is less than 0, it is a max, and I was trying to find a max. So therefore, x equals 6 is a max. I've got it verified there. Okay, step 5. I need to find my other dimensions. So we're going to find some dimensions. All right, and then let's see. I think I want to use the given equation. All right, so I've got an x squared plus what was that given? 4xh equals 108. All right, because I know what x is, so now I can start plugging in here. Let's see, x squared is going to be a 36 here. 6 times 4 is going to give me a 24 here. Subtract 36 from both sides. I think that's going to be like a 72. 72 divided by 24 is going to give me like a 3. So then I have a height of 3. Okay. All right. From there, we can write our therefore statement. All right. So now this was, let's go back and look at that box for a minute. Okay. These two sides are the same. And then my height. So when I write my dimensions, I'm going to write all 3 of them. All right, so a 6 meter by a 6 meter by a 3 meter will make a box with a maximum volume. So then there's your therefore statement. I think in the homework, honestly, I don't remember. There's going to be a few out of the book, I think, and then maybe 1 or 2. They will probably be pretty much exactly like these 2 examples that I've just done here. Tomorrow we'll do a different type of optimization, just different setup, different drawing. And then the second example we do tomorrow is going to be kind of rough. All right, so I'll start you out with the easier problems. All right, and then we'll move to the more challenging ones.